So you probably heard that square root of -1 is I, and it's an imaginary number. And it's called an imaginary number because there aren't any numbers that we can use as quantities that would satisfy this number. So what I'm trying to say is that this does not belong on the number line. Right? This doesn't belong on the number line. I mean, you can even prove it. So here's my argument of why I does not belong on the number line. So for example, if I belong to the number line, then there are three possibilities. I could be equal to 0, I could be bigger than 0, and I could be less than 0. Now this first one is immediately, it doesn't work, right? I is not 0 because for this to work, you need to satisfy I squared equals -1. That's what this means, right? To be the square root of -1, that's what it means. But then if you square 0, it doesn't satisfy -1. So that's a no-no. Right? Immediately, that's nonsense. So if I was to be found on the number line, then either it's on the right side of 0 or the left side of 0. Let's see what happens for each of these assumptions. So let's say I can be found on the right side of the number line. Then, if this was the case, then I could multiply I both sides, right? So I can multiply I both sides. And then what do you get as I squared?
-1.
-1. And what do you get as 0 times I? 0 times anything is? 0. So you get this. Does that make sense? No, it doesn't, because -1 cannot be more than 0. We know that -1 is less than 0. So therefore, this can't happen. Okay, so now it remains that the last possibility, maybe I belongs to the left side of the 0 on the number line. Well, then we can do the same trick. We can multiply by I both sides. But here we have to be a little more careful because we're assuming that I is a negative number. When you have a negative number that you're multiplying both sides, what do you have to do for the inequality? You have to flip the inequality. Whenever you multiply or divide by a negative sign on an inequality, you have to flip the inequality, right? So that's going to flip the inequality, and I get, again, I squared, which is -1, 0 times I, which is 0, and this is nonsense. So no matter which assumption you take, all of them leads to nonsense, which means this number, if it did exist, should not be on the number line. Okay. Now, there are two ways to go about this after finding out that it doesn't belong on the number line. One is to say, well, all the numbers that we know of should be on the number line, and since it does not exist on the number line, there is no such number. All done. We just ignore them. Okay? They don't exist. Okay? A second approach is, well, if it doesn't belong on the number line, let's just put it somewhere. So we just put it like this and say I belongs here. And that's a nice idea because if I belongs here, then 2i should belong here, -I should belong here. If all the possible multiples of I, that's perpendicular to the real line, right? Furthermore, if you ever solve equations like x squared plus 2x plus 2 equals to 0, the solution of this is not just a multiple of I, but it's -1 plus minus I, right? So you have a mix of a real number and an imaginary number. Such a number is called a complex number. And that can even be put on here as if you're putting coordinates. So think of this point as 1 plus I, because this is 1, that's I. So this would be like 1 plus I. And this point here would be 1 minus, sorry. Sorry, let me fix this, because I want plus one, right? Okay, so if you solve this with the minus sign, you get positive 1 plus minus I, and they can be found on this complex plane. So this, what you get is not just the number line, but the entire complex plane. Okay? And on the complex plane, you can denote all the possible complex numbers, a plus minus bi, or a plus bi. Anything that's of the form a plus bi can be drawn on this complex plane. Okay, so that's the second approach. But most of you here are engineers, and you might be thinking, this is nonsense. Like, we deal with real things. There's no need for this, right? And you would think, right? Then you go into your circuits class, and you end up using complex numbers all the time. Like, yeah. And you might be thinking, what? How can that be possible? Complex numbers don't exist. Why are we using complex numbers for real engineering type things? And the answer is that complex numbers can be thought as a way to denote some other quantities. So I'm going to talk about polar form a little later, but what ends up happening is that when you work with analog circuits with a capacitor and inductor and stuff like that, a lot of times the current that's flowing inside these circuits are AC currents. Okay, it's a alternating current, and alternating current looks like a sine graph and a sinusoidal graph. And if you want to quantify the analog, the alternating current that's flowing inside these circuits, not only they have the amplitude, but it also has the phase. And engineers found out that if you use complex numbers, then you can encode both at the same time. So it makes it very convenient. Not only that, you can even add two AC currents using complex numbers, and it just works. The math just works out so that it's easy to describe the alternating current inside the circuit. All right. So math is quite surprising because people come up with all kinds of math, and sometimes they look useless, but later you find yourself using it anyway. So that's what happens. Now, there's so many other kinds of math that mathematicians make these days that there is no application for at this point. But in the future, when engineering advances more, then it might make use of more complicated math as well. And I should also note that complex numbers are used in quantum mechanics. So when you try to do advanced physics, it's impossible to do the math without using complex numbers. I mean, it's doable, but it becomes 10 times harder. Making use of the complex numbers and its properties allows you to describe quantum state functions a lot more efficiently. Okay? So there are several use cases for the complex numbers. Okay. So that said, hopefully that was a nice motivation for you guys to learn complex numbers in this class. And after all, it was really the engineering professors who asked us to include complex numbers in vector calculus because they use it in the other classes. Okay, so make sure that you understand this content and learn it in a way so that you can still remember it. Remember how to use it in your other classes, okay? All right, so let's continue on. Some basic operations on complex numbers. Well, of course, if you have some operations, you can have addition, subtraction, all that, right? So you can have 2 plus 3i plus -5 plus 7i. Then you just add the real parts together, the complex parts together, and imaginary parts together, and that's what you get. And if you think about it, this is nothing different from, this is exactly the kind of thing that you would do if you added two vectors. If you have 2 comma 3 plus -5 comma 7, right? Then you would be doing -3 and 10. So there's like one-to-one correspondence between the two. And the scale of multiplication will correspond to multiplying a real number. So when it comes to addition and subtraction, it's basically saying that anything you can do with two-dimensional vectors, you can do with complex numbers. Okay. Number 2, you can subtract, which is not very different from here, but I'll just write it anyway. So you can have 1 plus 5i minus 7 minus 2i. And this would be 1 minus 7, which is -6. 5 minus -2 would be plus 7i. And you can do the same thing for 2D vectors. So this is 2D vectors. This is complex numbers. Now, what is surprising is that you can multiply complex numbers. Right? You can multiply complex numbers, and the way you do it is just FOIL. 1 times 2 is 2. 1 times -3 is -3i. Then 2i times 2 is 4i. And then 2i times -3i is -6i squared. But what is I squared? I squared is -1, right? Mm-hmm. So you can replace I squared by -1, and you can combine 2 with +6. 2 plus 6 would be 8, and -3 plus 4 would be +1. So if you combine these two as like terms, you end up with plus I. So you can multiply two complex numbers, but whereas addition or subtraction can be done with two-dimensional vectors, there is no counterpart in multiplying two 2D vectors. No such operation for 2D vectors exists that does the same thing as this. Okay? Of course, we have some other operations. We have the dot product, right? And if we embed the 2D vectors into 3D, then we can even have cross product, which will give you an element in the z direction. But both of those have nothing to do with this one. So you have this mysterious operation between two complex numbers that does not have any part in 2D vectors. And that kind of will motivate you to investigate this operation further to see what's really going on. So I will be giving you a better description of what multiplication of two complex numbers is really doing. That will be a big part of today's class. Or you can divide 2 plus 4i divided by 1 minus 3i. But if you recall that I is square root of -1, what you're seeing over here is really this, right? And if you have square roots in the denominator, you're told that that's not a good thing to have, and you need to rationalize the denominator. Okay, that's what you will have to learn. So when you divide a complex number by another complex number, the result should be another complex number, just like how we add two complex numbers, you got a complex number. Subtract two complex number, you got a complex number. We multiply two complex numbers and we got a complex number, right? So if you divide two complex numbers, you should still get something plus something I. So my question to you is, what goes here and there? How do you get those numbers? And the answer has to do with multiplying the conjugate. So let me put a note here. A plus BI bar is A minus BI. And this is called a conjugate, or the conjugate, Okay, so it's a conjugate complex number, and the idea of doing division is to multiply the conjugate top and bottom. So we take 2 plus 4i over 1 minus 3i and say this is same as 2 plus 4i over 1 minus 3i. You multiply 1 plus 3i, you multiply 1 plus 3i, top and bottom, because what's a conjugate? You just take the imaginary part and switch its sign. That's what a conjugate is. So because this is minus, you just switch the sign from in front of I to minus to plus. This is called the conjugate of this number, and you're going to multiply that top and bottom. Now, why do we do that? Well, you'll see what happens if you keep computing. And so we're going to multiply this top and bottom. And let's multiply the top again by doing the FOIL, just like how we did it over there. So 2 times 1 is 2. 2 times 3i will be 6i. And then 4i times 1 would be 4i. And then 4i times 3i would be, well, I squared is -1, and you get 4 times 3, which is 12. So you get -12. You get that? I squared is -1. That's why you get a negative here. And 4 times 3 is 12. And for this one, 1 times 1 is 1. 1 times 3i gives you plus 3i. -3i times 1 gives you minus 3i. And then minus 3i times positive 3i. Well, I squared gives you -1. There's a minus already, so that now that's going to make it plus. And then 3 times 3 is 9. That's what you get. Now, do you see that these two cancel? And once you cancel those two terms and simplify the top, it becomes -10 plus, 10i divided by 10, right? And now we can split the fraction into 2. And we can make it as -10 over 10 plus 10 over 10i. 10 cancels, 10 cancels, so you get -1 plus I. And indeed, the final result does look like a complex number, right? Yeah, a real number plus real number times I, right? So that's why you want to multiply the conjugate top and bottom. If you multiply the conjugate top and bottom, then you can simplify the division and be able to write down the result of the division as a complex number. Any questions? Alright. Okay, since most of you are making progress, let's do this together. Not that. All right, so you have 1 plus 2i, 2 plus 3i, and you're multiplying the conjugate of this denominator to both top and bottom. Okay, so take the conjugate of the denominator, you multiply it top and bottom, and you FOIL it out. So 1 times 2 is 2, 1 times negative 3i will be negative 3i, 2i times 2 will be plus 4i, 2i times negative 3i. Well, watch out. I times I is I squared. What's I squared? Negative 1. So you have negative 6 times negative 1, which is positive 6. Okay, and then this one you have 2 times 2, which is 4. 2 times negative 3i, negative 6i. 3i times 2, which is plus 6i. 3i times 3i, that gives you negative, well, 3 times negative 2 gives you negative 9, but I squared gives you negative 1. So this ends up being positive 9. Okay? And then if you gather the real parts, 2 plus 6 is 8. Negative 3 plus 4i is 1. And then these cancel. 4 plus 9 is 13. And your goal is to write down the answer as something plus something I. So don't leave your answer like this. Split them out and say 8 over 13 plus this is really 1 over 13i, right? I should be thought as 1 times I, right? So you have 1 over 13i as the answer to the first one. Okay. Let's try the second one. Yes.
No, never mind.
Okay.
Thank you.
All right. So you have you have the square root only over 3. So I is outside the square root. Okay. Now it's still possible to take the square root of I. It's not like impossible, but you have to distinguish the difference between having square root only until 3 or over until I. Okay. So right now I'm just having the square root on the 3 only. Okay. So I'm going to multiply the conjugate of the denominator top and bottom. So it's going to be 1 plus square root of 3i top and bottom. And let's see, 1 times 1 is 1. 1 times square root of 3i is square root of 3i. Square root of 3i times 1 is square root of 3i. Okay, and then square root of 3i times square root of 3i is square root of 3 squared, right?
Mm-hmm.
And then I squared, separately squared, and that's equal to negative 1, right? In the denominator, you have 1 times 1, which is 1. 1 times square root of 3i, or plus square root of 3i. This times this will give you minus square root of 3i. And lastly, this again is minus square root of 3 squared I squared. Square of the square root of 3 will just give you 3. I squared is negative 1, so on the top you get 1 minus 3, which is negative 2. These two are same, so it doubles. They double as 2 plus radical 3i. On the bottom, these two cancel. I squared cancels with negative, so it's a plus, so you end up doing 1 plus 3, which is 4. And in the same manner, you have to split this again. You get negative 2 over 4 plus 2 radical 3 over 4 I. And you should still simplify further. See, 2 and 4 can be reduced, right? How does that reduce?
Over 2.
1 over 2. Same thing here. 1 over 2, so it's plus square root of 3 over 2 I. That's what happens. So hopefully that was enough exercise to work with division. And along the way, we also practiced doing multiplication, so it wasn't that bad. Alright, so now, observe, if you have cosine theta plus I sine theta multiplied to x plus yi, you end up finding something that you've seen before. Actually, something that you've seen in the last class. Okay, let's do this. You get x times cosine theta. Usually you want to write down x cosine theta rather than cosine theta times x, because if you write down cosine theta x, you're not really sure if it's like this or this. They have totally different meanings, right? So it's really this one you want to write, but then you need a parenthesis, so it's not a good way to write. So you really just should put the x first. So this times this, I'm going to write x first and then cosine theta. Okay? And then when I do this, that's going to be, again, y times cosine theta. And even though this might be a little confusing, but always you want to put the I afterwards, okay? And then if I do this, that's going to be plus, yeah, I put I here. Okay, well, that's some exception. People write I sine theta in this case, all right? But that's going to be x times sine theta times I. And then when I multiply this, I squared gives you -1, so you just end up with negative y sine theta. Okay? Furthermore, if you collect the real part and the imaginary part, you get x cosine theta minus y sine theta as the real part, plus the imaginary part. Let's write down the x first, okay? The imaginary part, you get x sine theta plus y cosine theta times I. Okay. Where did we see this before?
Identity.
Well, if theta is equal to 0, that gives you the identity. And in fact, if theta is 0, what is that? You get sine 0, cosine 0 is 1, so it's just 1. Multiplying by 1 doesn't do anything, right? Yeah?
You rotate 90 degrees.
Not 90 degrees. Rotate by?
180.
No. Where do you see 90 or 180? I don't see anything of that. Yeah.
When you
We rotate by theta degrees, okay? So, or theta radians, because I don't have a, see, cosine theta degrees and cosine theta, if I don't have this, then this is in the radians. Oh, this is another thing that gets unnoticed. Okay, so let me digress a little bit. I have a question. Why do we use radians? Okay, let me make the question more clear. Why do we like using radians in the calculus class? Have you ever thought about that? Yeah, they just force you to use it. Yeah.
It uses pi.
No. Yeah.
Because like the sine function, the cosine function, they go
Yeah.
by pi amount of radians.
No. All right. So let me give you the answer. So this is something that your teacher may forgot to tell you. What's the derivative of cosine theta?
Negative sine theta.
Negative sine theta. That everyone knows, right? What's the derivative of cosine theta degrees? That's going to be negative pi over 180 sine theta degrees. Did you know that?
No.
Okay, so next time if somebody has TI Inspire or TI 89, put your calculator to degree mode and write down derivative of cosine. It's going to give you this strange thing in the front. And you might be like, where the hell did this come from? Well, see, if you look at the graph of the cosine, that's like this, then it looks normal, but only if you use the x-axis as in the radian unit. If you draw the cosine theta, where theta is degrees, look, degrees require a full 360 to do one turn, right? So the cosine only goes up to 1, right? But to reach 0, you need 90 degrees, so you need to go all the way here, and that should be something like 90 or maybe something. So it's a really wide graph. You see that? The slope is very small. That's why you get this number. Slope, see, pi is about 3. 3 divided by 180, that's like 1 out of 60. That's a very gentle slope. Why do you get that? Because if you use the degree, that's what you get. And that's really not nice, because anytime you differentiate, you end up with all this. How are we going to handle this, right? So that's why before learning calculus, in the pre-calculus, you learned how to work with radians, okay? They don't tell you why it's important. They just tell you that, and then now at some point, they tell you this is true, without telling you that if we were to use degrees, then you get this horrible number, okay? So hopefully, that's something that you learned for the first time today. Okay, so going back, because I don't have any degrees there, this should really be thought as radians. But that's beside the point. But what I was trying to get at is, in the last lecture, I taught you that the rotation matrix is this one: cosine theta, negative sine theta, sine theta, cosine theta, right? So that if you have any point on the plane, and if you wanted to rotate that, so if you had a point on the plane, and if you wanted to rotate this around by some theta angle to get this new point, then you just have to calculate this, right? Yeah. This point is like, if you do across down, you get x times cosine theta minus y times sine theta as the x coordinate. And then if you do across down, this is x times sine theta plus y times cosine theta, which is exactly what you see here. Okay. So what does this calculation tell us? It tells us a very interesting conclusion, which says that if you multiply by cosine theta plus I sine theta, the point will rotate by theta degrees. Okay? So what I'm trying to say is that, let's say this point is an arbitrary x plus yi in the complex plane. This is the I, this is the real, there's some complex number, okay? And then, if you multiply this by cosine theta plus I sine theta, if this is being multiplied to this, the result is that whatever that theta is, let's say this theta is over at this much, then this will be the cosine theta plus I sine theta times x plus y, sorry. In other words, multiplication in the complex plane has the role of rotation. Okay, the multiplication of complex numbers rotate things. Now, a well-known example of this is when theta is 90 degrees. Okay, so when theta is 90 degrees, what's cosine 90 degrees? What's cosine pi over 2? 0. What's sine pi over 2? 1. So you get what? I. You get I, right? Okay. So you get an I. So let's start with 1. If you multiply 1 by I, what do you get? You get I, right? Which is here. Is that rotated 90 degrees? Yes, it is, okay? Now, what if I take I and multiply by 9I again? What's I squared? You get -1. Is that rotated by 90 degrees? Yes, it is, right? Now you take -1 and multiply by I. What's I times -1? Negative I, so it's again here, which is again 90 degrees. Okay? And you can experiment with other things too. You can take some arbitrary point like 3, 2i. 3 plus 2i. Is this point, right? Now let's see what we get if I do multiplication by I, 3 plus 2i. That's going to give you 3i and what? I times 2i, what's that? I times 2i is negative 2. Okay? So that's going to be -2 plus 3i. Where is that? -2, 1, 2, -2, and plus 3i here. Is this 90 degrees? Yes, it is. Okay? So multiplication by I rotates everything by 90 degrees. And in general, if you have cosine theta plus I sine theta, multiplying that to any number will rotate the point by that angle. This is a very interesting phenomenon here. Okay? And that gives rise to the following concept. Polar form of a complex number. Okay. In order to define this, we first have to define something called the magnitude of a complex number, which is if I have a plus bi, you take the absolute value. That's defined as square root of a squared plus b squared, which is nothing else than the vector magnitude that we have always been using, right? So if this was the vector a comma b, what's the magnitude of that vector? It's this, exactly this, right? So we define it like that. And then a plus bi can be thought as, well, then let's do this first. You take any vector and divide it by its size. What do you get? Any vector divided by its size, its magnitude, you get?
A unit vector?
A unit vector, right? So then this is on the unit circle. See, I can't say this, I can't call this a vector because it's a complex number, but at least it will belong to the unit circle, right? Now, if any number belongs to the unit circle, then there's an angle theta from the positive x direction, right? And that can be written as cosine theta plus I sine theta. So if it's in the unit circle, then you can say that a plus bi over square root of a squared plus b squared is equal to cosine theta plus I sine theta for some angle theta. Okay? It's equal to that for some angle theta. And therefore, you can multiply by this thing here to the other side, and you can write it as a plus bi equals to square root of a squared plus b squared times cosine theta plus I sine theta. And rewriting a complex number in this way allows you to see what's going to happen if you multiply. So let me try to make that point by giving you this example. Consider 1 plus I, okay? Find its polar form. Oh, sorry, I should have said. This right side is known as the polar form. Writing a complex number in this form is called the polar form. Okay, so let's try to see how we can do this. So, solution first. How do you get the size? Size should be norm of a plus bi is square root of a squared plus b squared. Oh, by the way, notice that I don't have I anywhere in here. Okay, that's a common mistake. People include the I and you get I squared, which ends up giving you a squared minus b squared. But that's not the size. The size of a vector is always a squared plus b squared, not a minus b squared. A squared minus b squared. So using this, if I have absolute value of 1 plus 1i, that's going to be square root of 1 squared plus 1 squared. Okay? Be careful, you don't put I here. There's an I here. There is no I here. You get that? No I in the magnitude. And because 1 squared is 1 and 1 plus 1 is 2, you get square root of 2 as your magnitude. Okay? And then as for the angle, you just have to draw it. What is 1 plus 1i? It's this one, right? What is the angle?
45.
45 degrees. And we want to write it in terms of radians. So we should say that 1 plus I is equal to square root of 2 times cosine of pi over 4. 45 degrees in radians is pi over 4. Hopefully you know that. If you don't, please review your radians and degrees today, okay? And then I times sine of 45 degrees. Okay, yes?
That's cosine of pi over 4 and sine of pi over 4 read 2 over 2. Is that just like a coincidence? That they're, aren't they?
No, I mean, this is a special angle, so you know the exact value, right? And it turns out that it's square root of 2 over 2, square root of 2 over 2, right?
Mm-hmm.
And you multiply by the square root 2. Square root of 2 times square root of 2 over 2 gives you, this is just 2 over 2, which is 1, right?
Yeah.
So it recovers this.
Oh, all right.
It better be equal or else it doesn't make sense, right?
Yeah.
Yeah. So, that's a good thing, okay? Rather than saying it's a coincidence, it has to be that way, right? All right, so by rewriting 1 plus I as this, we now know what's going to happen if I take any random complex number and multiply by 1 plus I. If I just look at 1 plus I wouldn't have known this, but if I write it in the polar form, I see that first it's going to resize the vector or the complex number by square root of 2. It's going to make it longer, okay? And then it's going to rotate by 45 degrees. That's what the resulting number would be doing. Okay? So that's the geometric understanding of a multiplication by a complex number. Multiplication of a complex number is best understood as magnitude and angle. In other words, you have to change the complex number into polar form in order to see what it would do when you multiply it on other numbers, other complex numbers. Is that good? All right. So from here we can go to multiple directions, but just to end the discussion, let me give you a formula for converting to polar form. So, the formula for complex number is, a plus bi is equal to r times cosine theta plus I sine theta, where this we already know, r is the square root of a squared plus b squared. Again, no I here, please do not put I squared there, that's going to mess up everything. Yeah. I'm pretty sure I'll still see like 1 or 2 people in this classroom writing I squared thing exam. Okay, but hopefully it's not you, okay? Alright, so that's the first one. And then theta, we actually did this in the almost like the first class or the second class. This is really, the theta tells you the direction, right? So what do I mean when I have a plus bi and I'm rewriting in terms of r and theta. So r would be this length, that's the magnitude of a vector, right? And theta is the angle from the positive x-axis. So in other words, if you get a vector in a coordinate form, the polar form is merely asking what's the magnitude of the vector and what's the direction of the vector. We did this in like the first lecture or the second lecture, I can't remember, but we did that, right? So do you remember how to get the theta from A and B? How do you take the coordinates and get the theta from it? Anyone? No. Yeah?
Use inverse of tangent.
Yes, you get tangent inverse. And what over what?
Y over X.
Yes, that's very good. In our case, it's x and y, so b over a. Very good. But then there is a modifier because tangent inverse has a blind spot, right? Tangent inverse can only give you angles from negative pi over 2 to positive pi over 2. From negative to there. And that's often a problem because some numbers belong on the left side. See, this is negative pi over 2 until positive pi over 2. From negative 90 degrees to positive 90 degrees, the tangent inverse will successfully give you the value that you want. But on here, you get a blind spot, okay? So you have to modify this and put plus alpha. And the way you fix this is like, so where the alpha is, if it's on the right side, there's no need to change anything, right? It gives you the correct answer, okay? But if your complex number belongs to quadrant 2 or quadrant 3, then this is going to give you the wrong value, so you have to do a modifier, and the modifier here is you add a pi here, and over here you have to subtract a pi here. And then everything's good, okay? Let's just see how this thing works. So for example, if I had -1 and -i, so this is like -1 minus I. So that corresponds to when A is -1 and B is -1, right? What is B over A then? -1 over -1, that is positive 1. So if you apply tangent inverse, you're going to get positive 45 degrees. No, that's not good because I need it to be in the third quadrant. This is in the first quadrant, right? So how is it modified? You subtract 180 degrees to give you the correct angle, which is -135 degrees. In other words, if I use radians for this discussion, the tangent inverse of -1 over -1 is going to give you pi over 4, but you have to subtract by pi because this really belongs to the third quadrant, and the end result is you get -3 pi over 4. Okay? So that correctly fixes it. Now, this is not the only convention. There's a second convention where you can put, don't write this one down because you're going to confuse yourself if you see your notes later. But the second condition is you can also do 0 pi, pi, 2 pi. And the difference between this convention and this convention is this one will make your angle to fit between 0 to 2 pi, whereas this one will make your angle to fit between -pi to pi. Okay? So there are two different conventions. Now in the past, I've been using this one, but later I realized that this is not the one that I should be teaching you guys. I should be teaching you this one. And the reason for that is when you go to circuits and you describe the AC current using the complex numbers, the magnitude R will be the I max, where it's the maximum value of the current, okay? And this theta is going to be your phase angle. And the way you use the phase angle is you say something like it's 90 degrees ahead of the current or 90 degrees behind the current. Those are the languages that you use, which would only make sense if your angle is between negative 180 degrees to positive 180 degrees. You get what I'm saying? So you really want your angles to be between negative pi to positive pi in that context. So since you're going to use your complex numbers, especially the polar form in your circuits class, you really want your angles to fall between negative pi to positive pi, or in terms of degrees, that's negative 180 degrees to positive 180 degrees. Right? Okay, so hopefully that wasn't too bad. So erase all this. And you really don't have to write that example down. It's kind of clear just to have this, right? So how do you go from a rectangular, you call this a rectangular form, by the way, rectangular form, to the polar form? How do you go from rectangular form to polar form? Well, you first calculate the magnitude, R, and square root of a squared plus b squared. That's kind of obvious. But the angle theta, you have to use the tangent inverse function, which has to be modified because it has a blind spot on the left side. Okay. So to get the correct answer on the left side, you need these two things. Right? Okay. So here we didn't have to make use of that formula because it was kind of obvious that it's 45 degrees, right? But it may have made you feel a little uncomfortable because what if it's not 45 degrees? How are you going to get it? But over there you have an answer, okay? And once you have a formula, then it feels like it's less of a burden, right? Okay. All right. So let's make another remark. If you have, say, cosine A plus I times sine A times cosine B plus I times sine B. So in this case, both of the complex numbers belong on the unit circle. In other words, if you view these as vectors, they're both unit vectors, right? And you also know that multiplying this to another one will rotate this thing by angle degree A, right? Angle A. So here's what's happening. We have already some angle B, where this is cosine B plus I times sine B. And you're multiplying this by this thing, which is going to do what? It will rotate by angle of A. Right? So this is the new one, which is cosine A plus I sine A times cosine B plus I sine B. But then the geometry itself, if you look at the geometry, it suggests something. What is the new angle? Yeah, what is it?
A plus B.
A plus B, right? So just by drawing the graph, we see that this better be equal to cosine A plus B plus I times sine A plus B. Oh, okay, that's interesting. On the other hand, we can FOIL this out and see what happens, right? So let's do that. We can FOIL this out and see what happens. So we get cosine A times cosine B. forgive me for going all over the place. I only have like 5 minutes. I really want to finish this quickly. All right, so cosine A times cosine B, and then the next one is cosine A times I times cosine A times sine B. Yeah, that's the one. The next one is plus I times sine A cosine B. And then finally, I times I is I squared, which is -1, so you get -1 sine A sine B. Okay, so let's simplify this by dividing the real part and the imaginary part. The real part is this one. These two are real numbers, right? You have cosine A cosine B minus sine A sine B, together giving you the real part. And these two have I in there, so you get cosine A sine B. But for some reason, people like to write this one first. So I'm going to write this one first. I have sine A sine B plus cosine A cosine B times I. Okay, and because these two are the same, we now have a nice identity that some of you may have seen in high school, and some of you may not have seen it. But if you haven't, you end up using this again in your differential equations class, so it's good to memorize. Okay, so what do we see? Cosine A plus B is equal to what? Can someone read this? Tell me. Cosine A plus B is equal to?
Cosine A cosine B minus sine A sine B.
And then sine A plus B is equal to? Does someone else try?
Sine A sine B.
Sine A sine B
Plus cosine A cosine B I.
No.
No.
If this one has I, that one also has I, so they are matched. So this portion should equal to this portion, right?
Yeah.
Yeah, so there's no I there. Oops. How many of you seen this in high school? 2, 3 people. Okay. Maybe. Okay. I bet like half of you have seen this before, but don't remember. It's a standard thing that you learn in the trigonometry class. So if you took a course named Algebra 2 with Trigonometry, or if you took a course named Pre-Calculus, in one of those two classes, you've seen this before, right? But if you haven't, this is a pretty important formula that you should really try to learn, okay? So, as an example, let me say, for example, if you wanted to know cosine of 75 degrees as an exact value, then you can think of this as cosine of 30 degrees plus 45 degrees. And according to that formula, it's cosine 30 degrees times cosine 45 degrees minus sine 30 degrees sine 45 degrees. I got this confused. This is this. So you're going to end up with square root of 6 and square root of 2. So you get square root of 6 minus square root of 2 over 4 as the exact value of cosine 75 degrees. Okay. So you're going to use this later for some other purposes. These are important formula. We get this for free because we investigated the rule for multiplying complex numbers. Okay. So we're going to work on the pull from further in the next lecture.